Hello. Hello, Professor and Dr. Fasum.
Hello.
Hello. Actually, the schedule changes. Every session has to finish before 12 a.m. so that the closing speech will be at 12:10.
Okay.
So the closing speech for all session is at 12:10. So every session will finish in the morning. So we will meet in the general meeting at 12:10. There is a little bit modification in the schedule. Since in the afternoon.
Sorry.
But our program ends at 11:05, so we're good.
We are good, but there was a general meeting at 9:30 in the previous schedule. But now we'll meet at.
I think for us it's no problem. For maybe for other sessions they had afternoon presentations also. Yeah.
Okay.
We don't have after sessions.
We don't.
We don't have. But there was a general meeting, so we will finish in the morning.
Yeah.
Okay, the general meeting is the same link as the opening, yeah?
Yeah.
Daniel, it's the same link as for the opening session yesterday?
Quite. ሶስታችን ስለሆነ እያወራን እኮ ነው መግቢያው ስለሆነ ነግሬያችኋለሁ።
Professor, what's your area of research?
Right now we are.
You're muted, I think.
Can you hear me now?
Oh, yeah, I can hear you now. Yes.
Good. At the moment, I have two PhD students. One is working on crop diseases for coffee. Is working in the Ethiopian Artificial Intelligence Center, and another one is starting his thesis on cystic fibrosis. It's a very rare disease, and we have some doctors in Addis Ababa hospitals like St. Paul's and I think it's Tukura Bessa also, who have some background on this, and we're trying to set up a project at the moment. So basically, artificial intelligence in medical and biological applications, you know.
Okay, so yeah, so we align in research. So like I do like right now, just because I'm starting out as like an assistant professor, so I'm just trying to figure out like which way I'm going. So like I'm currently pursuing 3 directions. So one of them is AI application in health. So yeah.
That's why you're here. Yeah.
Yeah. Like I have like a few students working on that direction. Like yeah.
Yeah, we must pick up discussion offline. I wish I went to Addis this year, but I had plans, so we went online, but it simply didn't work out due to some private issues, you know. So one of those days we have to meet, and also I have plans on the midterm to go back to Ethiopia for teaching.
Oh, okay, good. Yeah.
So let's see. It's fine.
Yeah.
We keep in touch. Definitely.
Sure. Yeah.
So, do we have our first speaker now?
Our first speaker should be
Prophet Paul Adebajo.
Yeah.
Actually, Prophet Paul did not send his video and he's not present. Yep. So, yeah, we will start from the second presenter.
Dawit. Is Dawit around?
Dawit, but it says he's from Bardar. I'm trying to call him. Yesterday I saw him. He was in the attendees.
Okay.
So we'll start from Dawit.
Yes.
Good morning. Sorry. This is Samuel. How are you?
Good morning, Samuel.
Right.
Can I borrow Dr. Kutsum to another session because Dr. Bakal is missing? So, Dr. Kutsum, can you start the session for cybersecurity?
Cybersecurity.
Yeah.
Okay. Okay. Is that okay with you, Professor? Is there like some work you have to do until?
No, Chigarelem.
Okay. Okay. I will see you later.
Yeah, I wish you good luck with cybersecurity.
Thank you. By the way, that's one of my research areas that I'm looking into as well.
So, sounds great.
Yeah.
So, see you later. And we keep in touch, definitely.
Hello, Professor. I'm
Hello.
Daniel. Hello.
Hi, Daniel.
Actually, David is not also here, but we have his video. So, shall I start playing his video?
Yeah, let me give a short introduction. So, unfortunately, we missed the first presentation of Prophet Paul Adebajo. So, we now come to David Shibaba. He is with Barda University, and due to this internet problem, he cannot join right now. But we are now have his presentation as a video, pre-recorded video on predicting perinatal mortality based on maternal health status and health insurance service using homogeneous ensemble machine learning methods. So, Daniel, I would like to ask you to start the video. Thank you.
Okay, hello, my name is David Shibabo, and I'm PhD student at Department of Data Science from Bahardar University, Institute of Technology. First of all, I'd like to thank organizing committees of PanAfricon AI Artificial Intelligence Institute, and I'm going to present entitled, which is Predicting Prenatal Mortality based on maternal health status and insurance service using homogeneous simple machine learning algorithms. Authors are those, and those are presentation outlines that I have tried to discuss on or try to present on my presentation. As introduction, it is prenatal mortality is a period which is all about leading to births up to before birth up to 28 weeks and into 7 completed days after the birth. And as report shows that over 130 million babies can be born every day. Among those, 10 million babies are dead before celebrating 5 days the born, and almost 8 million can be the first day of the birth. According to the report, World Health Organization report in 2019, 133 million newborn babies infants can be alive each year. Among those, 2.8 million can be the first week of the birth. And this is most probably, or this case is mostly occurred on, which is 99% of these cases occurred on middle income level countries, which is near to more than us in sub-Saharan African countries. To reach out the Millennium Development Goal of Stage 3, international community can support low middle-income countries their renewed commitment in reducing infant mortality rate, improving by prenatal health service. Over 100 million individuals can pay pocket or payment get treated with difficulties of 10 millions of people, resulting in increased mortality. This is leading to the poverty cause of major cause of poverty can fill in on ill and barriers of accessing the health care when they can be needed. This is most probably a problem of financial issues. As in order to overcome the financial issues, to access at real-time health access for those pregnant women, health insurance service can be a resource pooling service, which can improve health care delivery, and community-based health insurance services, improving the accessibility to health, which can reduce financial risk, which is meantime. And we employ the machine learning algorithms in order to be diagonal or in order to be analyzed or process large data in order to get insights. As statements of problem, according to the World Health Organization, which is the report 2019, prenatal mortality is most case which is mostly occur in Africa, which is mostly common in Ethiopia, which is 68 per 100 pregnant women can be interpreted. That means days during the delivery of service or days during the born, which is it's mostly attributed to home deliveries, which can be account more than 85% of the prenatal mortality days can be due to the lack of awareness about health insurance. As you may show that a mother can be born twin babies or twin babies in home without any attendant of patients or without any healthcare services. As a result of financial service such as insurance service can be addressed the demand supplies that can be affect the availability of the maternal health, which is Ethiopian Ministry of Health can be working on for years of service to be accessible women through the community-based intervention in order to be increase newborn survivability and prenatal. This remains the common issue in Ethiopia, particularly home deliveries can be the most challenge of Ethiopia, which is still now 75% of women can be born outside health facilities. This is due to the health facility problem or financial problem. In order to be overcome, overall prenatal mortality can be reported from the hospitals. Studies that can be range of 66 up to 124 per total of 1,000 baby borns. There are a lot of researches that can be conducted on the same areas. Let me try to see what are the researches and what are the gaps that we have tried to researchable or what are the problems or that what can be researchable. For example, the researcher like Bakale can be conducted a research on to analyze community-based insurance service to utilize the healthcare. As research use both qualitative and quantitative, and researcher can apply on like logistic regression. And when it comes to the model deployment, risk factor can be identified really. Predictive model cannot be designed. Generative rules cannot be also designed. Artifacts cannot be designed. Model cannot be even deployed. And as the researchers also come to the same problem, which is most of research background on health, which can be really identified research factors, not develop model or deploys model or design artifacts. The another researcher was Nian Nguyen, sorry for correctly pronounced, evaluate statistical and machine learning methods to be predict risks of hospital children mortality in Uganda. And as model methodology, researcher can obtain this logistic regression, random boost tree, random forest can be adopted, whereas risk factor cannot be identified. Predictive model can be developed early. Generative rule cannot be generate rules. What are the rules that can be supported for policymakers or practitioners of the health workers? Cannot be designed. Artifact and model cannot be deployed. At the same time, Kumbdalala with another researcher which can be evaluate machine learning models and predicting risks of children mortality in South Africa. At the same time, model was developed but not yet deployed and designed any rules for these practitioners. But all of the previous research, that literature that we have tried to present previous slide, can be used local data, which is limited for geographically, like single city or town, and limited amount of data can be employed within limited data. We cannot be even design rules because of within the small data. We can machine learning itself was data intensive, so they employed a small amount of data, focus on determinant factors, especially for those statistical and health practitioners can identify risk factors only. And most descriptive statistics, descriptive statistics, rather than machine learning, itself one of the input for descriptive statistics, one of the input for machine learning or machine and use cross-sectional studies, which can be like cross-sectional or specific area, which is limited area, which cannot be extract hidden patterns from the data. That means like p-value and other statistical methods can be used, but it cannot be extract hidden patterns of knowledge from the data. This does not include some of the features which can be most important for prenatal mortality, like previous health birth history, community-based health insurance, and preterm history cannot be incorporated on previous studies. Due to this reason, we are going to come up with these gaps and to be researchable. Most of studies do not be developed predictive model, most of, but not all of, and most of the studies cannot be designed artifacts, which is used for for domain experts, cannot be deployed model and cannot be generated the rules for the policymakers. As research question, at the end of the research, we are trying to address those questions. What are the underlying structures and evolutions of prenatal mortality over time? Which homogeneous similar machine learning can be effectively predict the prenatal mortality? What are the determinant factors of prenatal mortality, especially in the case of Ethiopia? What are the important rules that can be generated from predictive model? Those are the research questions as general objective. This is general objective of to be developed the machine learning model to predict prenatal mortality based on maternal health status and insurance service. In order to come up with break down the general objective into specific objective or into specific, we try to capture to describe underlying structure of prenatal mortality over time, identify risk factors prenatal mortality in Ethiopia, to build model for prenatal mortality, to generate rules for the intervene the policies and implement, to deploy the model on the easy usage of model domain experts. Significance of study mostly significant for economical preservation, and Ministry of Health can be mostly usable, and different organizations like practitioners and nurses can be mostly used for model, and research can be used for finally reference. As a method, we use design science research. Since design research is one of the design research is for communication, that's why we are going to deploy the model. We use design science. We review literatures, which is nearly graphic health survey from which is collected from 2021 up to 2019, which is Gregorian calendar. This survey is collected for 5 years interval. We process data pre-processing value. We can understand data by using data visualization. We can clean data by using data cleaning techniques. For example, in order to handle the missing value, we use mode and median. For most of the data was categorical data, so we use mode and median. To handle redundancy, we can easily remove the redundant data, which is not important for machine learning. For data integration, we can use data integration, which is vertical integration, which is similar data, which is categorical textual data. So we employ vertical integration, which is total of 1,953 one total instance. For data transformation, we use discrete data by using binning method. To be handle class imbalance, which is class imbalance problem is also in our data. So we employ the minority oversampling. Synthetic minority oversampling techniques can be adopted, which is more after applying smooth, which is systematic minority oversampling technique, we obtained 140,659 total data for model. For after we get the quality of data, all data or one instance cannot be important for the model development. So we try to identify the features, or by using feature selection technique, one of the filter, which is chase square and mutual information, and wrapper, which is forward and backward wrapper selection techniques. Backward feature selection technique was for better, and one total of 17 features are employed, and domain experts can be recommended. We can split also data into training and testing by using random sampling technique, and we can also use tuning, parameter tuning, which is grid search technique. We can search grids from which parameter is given from the given data, from the given model, which parameter is best work. We can also tune parameters by using grid search. We can also develop the model, which is predictive model, and we can apply or adopt, or we can employ the data model for the model development. Gradient boost, random forest, and cut boost, and we can also identify risks after developing the model, which is using feature importance technique. We can also generate rules by using model performance evaluation technique, which is best performing model, which in our case, which is gradient boost, is best performing model. And we can also evaluate the models by using objective and subjective. By objective, by using evaluation metrics, model evaluation metrics. By subjective, domain experts. And we can also design artifacts by using HTML for front-end and Python for backend, which is Flask framework. We can also deploy the model on the Heroku Cloud platform for the model for users of domain experts or real-world scenario. This is the model architecture, how model can be worked. We can also pre-process data under those pre-processing techniques, and we can select the features by feature step backward select feature selection technique was work better, and we can split the model. We can also adapt, or we can also employ the models like random forest, gradient boost, cut boost, and we can also tune parameters by grid search. And we can evaluate model by using evaluation metrics. If model is best work, we can also select the model. In our case, gradient boost is best performing model. After all, we using gradient boost, we generate rules, identify risks, and finally, those generated rules and identify risks can be evaluated by domain experts. And those model, which is best performing model, was deployed on cloud platform, which is for potential users of real-world scenario. For model deployment and result discussion, in our case, the accuracy of gradient boost was 90.24% of accuracy, and remaining are lower accuracy. And when you try to compare the recalls of the given all models that can be employed in our, which is gradient boost, cut boost, and random forest, 99.7% of recall was achieved by using gradient boost. So we prefer gradient boost is, in our case, best performing model. So by using gradient boost, we try to identify risk factors, generate rules, and deploy the model. These are overall picture or pictorial representation or data visualizations of underlying structures or evolutions of mortality, which is, it is as you have seen, which is like in legit alive and not alive, which is a color indicates. Over time, it is reducing because of hospitality and other health insurance service can be increasing. And when you try to compare rural and urban, most deaths can be occurred on rural due to the health facilities and insurance service. And having health insurance service and without health insurance service, uninsured are more deaths occurred than that of insured. Those are determining factors of prenatal mortality, which is most attributes that can be selected by feature backward selection technique and domain experts. These are most determinant factors of prenatal mortality. These are generated rules. This can be how rules can be working, or in order to be enhanced, or in order to be understood the models by using like domain expert. This is generated rules by using gradient boost. That means this architecture or graphical representations of model was generated this like if pattern, this one. Finally, those rules are correctly identified, child can be alive. When it comes to third, child can be dead if the rules are not fulfilled. This is a rules which is generated from these graphical representations of terrorists. Finally, we deploy the model on model deployment, which is like on cloud computing platform like Heroku for the reward scenario. And we can also deploy the model, which is front-end HTML and back-end Python, which is Flask framework. And we can evaluate model by model in the risk, all of risk factors, rules, artifacts, and deploy the models by using domain expert. Overall scores of domain experts that can be identified by risk factors, rules generated by model, and deploy the model. Overall, the acceptance rates of the model was 88.4% of subjective evaluations of by domain experts. And we can deploy the deployed model can be evaluated and tested by collaborations of domain experts, which is domain experts come from Gondar University Referral Hostel and Bada University Referral Hostel. As we have discussed, these experiment results, proposed model was achieved overall performance of 90.24% of overall accuracy by using.
So I think the video is finished. So we virtually thank the author for the presentation. Yeah, another very interesting topic in medicine. Since we cannot ask direct questions, I think we proceed in the same way as yesterday. So this session is being recorded, and whatever question we ask will be reviewed by the author and can be answered remote. So I would like to ask you to provide your questions or comments or recommendations. Everything is welcome in the sense of a good critical scientific discussion. So if you want to say something, please raise your hand and you're going to be admitted by Daniel to ask your question.
Hello, Dr. Futsum. Welcome. Dr. Futsum?
Dr. Fitzum is back, it seems.
He's back, yeah. So if he has a question, also he can join us.
Yeah, thanks for the...
Yeah, they threw me out of the other session.
Okay.
Yeah,
okay.
Maybe because of the security leak.
Yeah, I think so. I'm sorry, like I came in like in the middle of the presentation, so I did not follow the entire one. So I'm sorry.
Okay.
Yeah. So is there any comment or question from the audience? Well, as a teaser, I can just mention an observation. On the page 4 of his presentation, he was reviewing literature. And there was a literature number 4, which didn't look good. It had like 55% accuracy. And that reminded me to calculate what happened if I take the case of Ethiopia. I have 68 out of 1,000 fatalities under this perinatal period definition. So that is 6.8%. So if I just take a statistical algorithm and I predict every baby will be healthy, then my false negative will be 6.8%, which gives a very good accuracy. So if you just take a statistical model, you certainly become far better than 90% accuracy. And I think it should be mentioned that simply the goal has to be in the area of, let's say, 98, 99% at least in order to get something useful out of the model. And I saw that the comparison with the experts was 88.4%. So that means there's still some work to do on the prediction. but maybe I took something wrong. So I just want to mention it and offer a discussion if you so like. So maybe Dr. Fitzum can take over and ask for questions.
May I ask like a summary of what the paper is about?
Yeah, you can. Yeah.
The paper, will you give the summary? Dr. Fitzum?
I was asking Professor you, like, because I came in the middle, but I didn't follow the entire
That was
thing.
what I was thinking, yeah. So the paper is about predicting perinatal mortality based on the health status and the data from health insurance services. And perinatal mortality is defined on the interval between 28 weeks before birth up to 7 days after birth. So each fatality attributes to this perinatal mortality. And the author was saying that in Ethiopia, the fatalities are 68 out of 1,000 cases. So that means that 68 babies during this period don't survive. And it also was mentioned that 75% home deliveries will contribute a lot to this problem. All right.
Yeah, okay.
And he was doing a literature review, and also he was investigating.
Sorry for the interruption. I think David Shibabo is online now. David Shibabo.
Okay, very good.
The author. Okay. So, yeah, I understand. Thank you for the summary, Professor, because like now I can formulate my question. So the so I was thinking, like, so if I understand it, that he was trying to see if there is any like link between health insurance versus prenatal child disease, right? So, and he was showing that like there were like less disease with parents that have health insurance, and the vice versa, right? So the question that I have is, can there really be a direct correlation between having an insurance or not? And if so, why would that be? Daniel?
Hello, Mr. Dwight. Are you there? Mr. Dwight?
Yeah. I'm hearing you now. Sorry for interruption.
Okay, so we played your video, so just answer the questions that are raised by the evaluators.
Sorry for late joining. Could you repeat the question, please?
So the question I have for you is, so are you trying to figure out if there is any correlation between parents having health insurance and prenatal disease, right, in that specific study region?
Yeah, first of all, the main thing that is economical issue related to prenatal mortality. The period prenatal mortality is which is pregnant women from before birth 1 month and after birth for consecutive 7 days, which can be delivered at the health facility. So especially when try to compare and contrast the rural and urban areas, the covering or the providing the health facility for the right time is.
Hello.
Did we lose him?
Hello. Hello?
I think we
Hello?
lost him.
Yeah, he's from Barber. Yeah. Okay, continue.
Uh, okay, I
I
think
think
we should
we lost.
continue to the
Yeah.
next speaker, right?
Okay, so you have raised your question. It is recorded, so we'll manage to.
Yes. Like
Yeah.
these are the questions, like the questions and the comments given by Professor Kim and myself. I mean, he can use later on to like
Okay, thank you.
address
So we
it.
can proceed to
Yeah.
the next presenter, which is Ahmed.
Yes.
He's not also present, so I'll play his video now.
Okay.
Okay.
Um, yeah. Good morning, ladies and gentlemen, esteemed members of the Pan-African AI Conference and fellow researchers. It's an honor to stand before you today and share our pioneering research on generating synthetic brain tumor images using StarGAN3 for lower class enhancements. So, medical imaging has and still plays a crucial role in diagnosis and treatment of deadly diseases such as brain tumors. But before we jump into our research and technicalities, let's take a step back and delve into why the simulation of brain tumors is absolutely crucial in the context of medical imaging research. So, brain tumors represent a formidable challenge in the world of medicine. They come in various forms, each with its unique characteristics and complexities. As you can see here, we have 8 different types or entries of brain tumors with different sizes and shapes. And the critical importance of simulating brain tumors can be summarized in a few key points. They are enhancing diagnosis and treatment planning. So, how does it enhance diagnosis? Basically, accurate simulations enable the development and validation of advanced diagnostic tools. They help clinicians identify tumors earlier and with greater precision, potentially saving lives. Regarding the treatment planning, the simulated data allows for the exploration of different treatment strategies, enhancing the planning and delivery of therapies to patients. So, moving on in our journey today, we will explore a solution to a profound challenge in the field of medical imaging. As many of you are aware, accurate and diverse medical imaging datasets are the lifeblood of cutting edge research, aiding in the development of innovative diagnostic tools and techniques. However, a specific challenge persists, one that our research strives to address. So, brain tumors, with their intricate nature and multitude of variations, present a unique set of odds for medical imaging researchers. The challenge we face is the need for precise simulation of brain tumor data, which is essential for the advancement of medical image enhancement techniques and diagnostic tools. Unfortunately, obtaining a sufficiently extensive and varied data set of real brain tumor images for research purposes remains a formidable task. So, our journey today begins with a fundamental challenge, a challenge that resonates with researchers and practitioners in the field of medical imaging. We are confronted with the need for accurate and diverse brain tumor data. So why do we need brain tumor data? As I said earlier, we have diagnostic tools and classifiers to classify whether a person has a brain tumor or not. And in order to have a high accuracy, we need to have access to a large data set of diverse and uh, of different types data sets. So the problem with the real world is that we have only 2 publicly available online datasets, the BRATS 2020 dataset and the brain tumor dataset. And the challenges that we will face in our approach is that we have to ensure that the synthetic images are realistic, representative of various tumor types, and addressing the class imbalance. So jumping on with the issues with existing brain tumor datasets, as I said, we have limited datasets that have class imbalance and also have lack of annotation. As I said, we have only 2 publicly available online datasets, so that shows that we have limited data. And class imbalance means basically that we have a huge gap between the number of brain tumor samples and healthy brain samples. And a study had been made in India a year ago that showed that the Indians had an 0.003% of its population that had only brain tumors. So that's a very low number of brain tumor images, and also most of them won't be publicly available online due to privacy concerns. And of course, we have a limited variety of brain tumors because datasets often have a narrow scope in terms of tumor types, sizes, and etc. To address this critical challenge, we embarked on an innovative journey that combines the power of artificial intelligence with medical imaging. Our methodology centers around the utilization of StarGAN3, a remarkable generative model, and the current state-of-the-art generative model. So the dataset used in our experiment was the brain tumor dataset. It is available on Kaggle. It has 155 brain MRI samples. So that shows the lack of large data. We have only limited data of 155 samples. And regarding pre-processing, we resized the images into 512 by 412 pixels, as they have to have a shape of a square, and also converted the images into the RGB format and PNG format in order to be able to feed them to the generative model, as the StarGAN3 accepts images in the RGB and PNG format, and as I said earlier, of course, in a square pixels. And regarding the model configuration, we use a pre-trained StarGAN3 AFHQ512 model and fine-tuned it for brain tumor data. We also incorporated the adaptive normalization for enhanced style control. And why did we use the AFHQ512 model or a pre-trained model? As it would be way faster, and we would have we will have only to fine-tune the last layer in order to generate brain tumor data. And I'll explain that in a bit. So that's the data set I used. It had 3 types of tumor: glioma, melanoma, and pituitary. Moving on to the pre-trained model. So this is the AFHQ512 model. It's basically 412 by 512 pixels, and it generates images of animals, as you can see here. And we changed that, or we used this model as a means of transfer learning in order to have a faster and more accurate and more stable training. And we simply fine-tuned it by removing the last layer of this model, of the AFHQ512 model, and imported our layer to generate brain tumor data rather than animal faces. So StarGAN3 has 4 main features. It has progressive growing, which basically means that it starts by the simple form of generating a 4 by 4 pixels, and then 8 by 8, and then 16 by 16 until you reach your desired pixels. And the adaptive normalization dynamically adjusts featured statistics for greater style control. PatchGAN discriminator basically focuses on image patches to improve local detail detection. And the WGAN loss function, it's basically the same as the normal loss function used for GANs, but it improves training stability and conversions. So this is the architecture for the StarGAN3 model. This is the mapping network. Mapping network is basically a network that passes the noise into each layer of the StarGAN3 in order to have the sense of diversity for the generated images. As in the normal gen architecture, you only feed the noise to the generator at the beginning of the architecture, and basically as you move on along layers, you basically lose the sense of diversity. So this mapping network basically passes the latent or the noise to each and every layer in order to have the sense of diversity. and then you'd find the RGB format. And then basically these are the samples, the leak value, and the upsampling and downsampling of the images. As I said, from 4x4 to 8x8, and etc. And these are basically the convolution layers. So moving on to the evaluation of synthetic brain tumor images, we used two of the highly known metrics, which are the Fisher inception distance and the kernel inception distance. So the FID basically uses features from the inception V3 network to compare distributions of real and synthetic images, while the KID uses the kernel methods on inception features to compare real and synthetic images. So basically, the main difference between both metrics is that one focuses on the distribution of real and synthetic images, while the other focuses on the image itself. Or means the feature of the image itself. The FID and KID have a strong mathematical foundation, but we don't have to jump into that. We only have to know that the lower the FID and KID, the more realistic and the better and high quality the image is. So we conducted 3 experiments. The first experiment we used a gamma of 6.6 and a data set of 310 images. So basically, we mirrored our images. We have 155 images, and we mirrored them. So we have 310 images. And for the second experiment, we kept the images the same, but we increased the gamma to 8.2. And for the third experiment, we kept the gamma as an 8.2, but we reduced the data size to 155. The rationale behind these 3 experiments was to check and to experiment the changes of the gamma values and the data sets and check how they will affect the generated images. So basically, the rationale behind choosing this gamma as the base for the first experiment was because I searched a lot of papers that said that for a 512 pixels, a gamma of 6.6 would do the trick. But then we changed that to 8.2 as we did the second experiment, as we found out that the 6.6 didn't do much well, as we would see in the results. So the 8.2 was chosen as I read the configuration of the StyleGAN3, and they said that an 8.2 would be the optimal solution for a 512 by 512 pixels, so that's why I used it. And then finally, we reduced the dataset size to 105 images, basically the half, to also see how that would impact the model and the generated images. So jumping on to the results, this is the first experiment results where we had the gamma of 6.6 and the dataset of 310 images, as you can see here. We can see that the FID and KID started as high as possible as the model was still training, but as we moved on along epochs and ticks, basically a tick means that the model was trained on 40K images. So that's 40K, 80K, 120K, and then 160K. As you can see, it did well for the first 40K images, but as we moved along training, we can see that the FID has diverged again, meaning that the model was unstable and it started to produce less realistic images. And as we can see in the KID, it shows that as well. It started as a high value as the model was not trained, and then along training it went down to nearly 0.2, and then it diverged again into basically 0.14, showing or indicating that the images generated were not realistic as possible. That's why we increased our gamma values into 8.2. And as you can see here, it started as well with the KID as high values. And then along training, we can see that they both stabilized. So reaching a value of 67 for FID and a value of 0.0134 for the KID, meaning that we generated a high quality images and of realistic and realistic images. And in the third experiment, we can see as well that the images converged and stabilized into nearly a same number for the 4 epochs, and here as well. But the difference between the second and third experiment is that in the third experiment we reduced the dataset size to the half. So we had a higher FID and KID. So this we had an FID of 76 and a KID of 0.183. So that means that the images are also realistic and of high quality, but they are not as realistic and high quality as the second experiment. So the here are the visual results of the 3 experiments. As you can see, this is the first experiment. We can see that there are certain brain tumor data or images that are not realistic. We can see that they are not complete as well. And for the second experiment, we can see that we have diverse images of different brain tumors, which yields a great result, and that's exactly what we want to achieve. And for the third experiment, you can see also that it generated large images of high quality and diversity. But as we can see here as well, that there are 2 images, for example, that they aren't that realistic. So we can say that experiment 2 and 3 succeeded into generating high quality and diverse images, but experiment 2 had the edge as it had more brain tumor data to train on. Basically, the key findings is that the higher gamma improves image quality, as we saw that increasing the gamma from 6.6 to 8.2 improved the FID and KID scores, indicating better image quality and realism. And of course, more data improves image quality, as increasing the dataset size from 155 to 310 images resulted in lower FID scores and more stable training. So in conclusion, our research demonstrates the potential of StarGAN3 for generating high quality and diverse synthetic brain tumor images. Manipulating parameters like gamma and dataset size allowed control over realism and diversity, and further optimizations could improve accuracy. Our work showcases synthetic data generation for overcoming limited medical image datasets. Future work might be recognition techniques, like we could incorporate advanced recognition techniques like spectral normalization and gradient penalty to improve stability and diversity. And we could also use semi-supervised learning. We could utilize the generated data with limited real data for semi-supervised learning to improve model performance. And thank you so much for your time.
That was a very interesting topic, and I appreciate the author for making a really nice video about their work. So if the author is around, we would like to address our questions directly to him. Otherwise, we will do as we did earlier and discuss about the work. So in this work, the authors did try to augment their data set to have more data for further training and analyzing of brain tumor detections, and so they went to use generative adversarial networks to generate more data, more accurate data, and they showed us how they did about it, the techniques they used, and the parameters they selected to ensure that to have good quality generated data. One thing that I found fascinating about this work is that they tested to see if the model they developed can also be trained using fewer data than that is present to see if it does well, and it showed that even if it is not quite as good as the data that was the model I was trained on, like larger data, it was still doing well. And this is fascinating. A question that I have for them is like, it felt weird for them to change a grayscale image into a RGB scale for this training. I don't know why that is needed. And also another weird thing is like transfer learning from an image that generates tigers and dogs or something like that to a brain tumor. So that was a bit fascinating. So like if ever, I would like to hear about what that is, why they chose that. Anyways, so if anyone wants to add their questions, the floor is free. Professor Akim, do you want to go next?
I think I don't have direct questions to this topic at the moment. Well, transfer learning, is usually you have to use what's available, and in today's world, we have so many trained models on cats and dogs that people just love it. Possibly, usually you have to compare a completely new training of your model versus a transfer learning. Maybe they did that and decided to go for transfer learning, but they also can answer this, of course. No, I don't have any more questions for this one.
Okay. Anybody else? Anyone? Anybody? Okay. In that case, I think that would be all for this presentation. Dr. Saye is saying it's a good paper. If you can talk and say something about it, can I ask the moderator to allow Dr. Taye to speak? Oh, you don't have? Okay.
Actually, Dr.
Daniel,
Taye, if you want to talk, we cannot do.
Yeah.
Cannot do in the presenter session.
Please
so,
do. Please do.
Okay, we still have time for the first session left, and I see that the next presenter, Yaha Hazani, is here. So my suggestion would be that we continue with the last presentation and just skip the tea break. The time is almost there, and why not just finishing this session by having the talk immediately? This would be my suggestion. So I'd like to ask Daniel to get in the speaker for the next presentation and ask him if he's willing.
Taye is now on the presenter list.
Yeah.
Okay, so let's first hear for Dr. Taye.
Yeah.
Good morning, everyone. How are you doing?
Hi, how are you?
Good. Nice to meet you again. The paper is very nice, especially in some of the areas where we lack the good size of data. Then applying such a technique is very good. So I hope the participant will come to know, especially wherever they need to generate the data from some basic few in number data, then there is a possibility. Because I have seen this paper, the same paper, either from Professor Hakim's student or Professor Friedelm's. Last year also we have the same papers which is related to this. So I think this is a good paper. most probably we will come to read it maybe when a full paper is submitted before proceeding to the publication. I just want to say my impression about the paper. Thank you so much for the.
Yeah. Thank you, Dr. Taya.
Yeah, thank you.
Okay, shall we present to the next presenter, or
Yeah, please. I would simply suggest to
the
go
next
ahead.
presenter? The next presenter is Mr. Yahaya. He's in the attendance list, so he will continue his presentation.
Okay, let me just introduce Mr. Yahaya. He is from Makerere University in Kampala in Uganda. So very happy to have him here today to talk about prediction of the effect of human immobility on COVID-19 cases transmission. And for this, he's using a hybrid ANN CNN model. So this will be our final presentation for this session, and I wish you good luck for this. So Yahaya, are you ready to give the presentation? You are still muted, but you are enabled to present now. Hello, Yahaya. If you are saying something, we cannot hear you. You are muted. Oh, maybe he's doing the tea break.
Mr. Yahaya, are you there?
Hello, Yahaya, are you there? That doesn't seem to be the case. So let's have our tea break according to the designated schedule. Let's reconvene at 10:40 and see if Yahaya will be able to present by that time. So 10:40 we reconvene, which is 9:40 in Europe and South Africa. Sorry.
Before we leave, the Dr. and the Professor, are you listening to me?
Yes.
Okay, the ending session will be held at 12:20 a.m.
12:20.
12:20 a.m. So
yes.
Dr. Taye told me to tell you that to present in the meeting session, in the ending session.
Okay.
Yes.
Okay.
So it's
so we will meet after the break at 4:40.
10:40.
Yeah.
Yes.
Yeah.
10:40. Okay.
That is correct.
10:40.
Yes. Yes.
And
Okay,
Daniel,
thank you.
Atto Daniel, just for the closing session, it will be the same link as for the opening session.
Okay.
Or which
I'll
link
ask
shall we use?
the other coordinators and I'll tell you after the break. I'll ask them. Okay.
Okay. So we'll meet at 10:40. Thank you.
Okay. Thank you.
Yeah.
It is the opening link. He told me now. It is the opening link.
Very
the
good.
link
Thank
is
you.
the opening link. Okay. Thank you.
Good. Thank you. Ciao.